We are going. The history of this agency is marked with broken barriers, once viewed as impossible, with science fiction turned reality, with innovations that have spun industries all their own, and with demonstrations of peace for all humankind.
We soar in the skies of our home planet. We maintain a human presence just outside of gravity, and we touch points all across the solar system and beyond. We're going back to the moon, and this is why.
The moon is a treasure trove of science.
It holds opportunities for us to make discoveries about our home planet, about our sun,
and about our solar system.
The wealth of knowledge to be gleaned from the moon will inspire a new generation of thought and action.
Without fail, every major program and mission NASA has invested in has led to technologies and capabilities that have shaped our culture.
The breakthroughs of the Artemis era will define our generation and the generations to follow.
The tens of thousands of jobs associated with propelling us to the moon today are just the beginning of a lunar economy that will see hundreds of thousands of new jobs develop around the world.
This is not an ambition of one entity or one country. The exploration of the moon is a shared effort,
woven together by a desire for the greater good.
Why the moon? Because the missions of tomorrow will be sparked by the accomplishments of the Artemis generation today.
Because the ambition to go has already begun.
And because Mars is calling. We need to learn what it takes to establish a community on another cosmic shore. So let's camp close before pushing out.
And so, we go to the moon now, not as a series of isolated missions, but to build a community on and around the moon capable of proving how to live on other worlds.
We'll use the lessons from more than 50 years of peaceful exploration to send a new generation to the lunar surface to stay.
We will anchor our efforts on the lunar South Pole to establish the Artemis Base Camp,
positioning us for long-term science and exploration of the lunar surface.
We will prove what it takes to assemble a complex ship in deep space.
We will perfect descending down to and returning from a distant surface.
We will learn how humans can survive and thrive in a partial gravity environment.
With improved spacesuit designs, mobile habitats, and with reconnaissance robots pre-positioning and relocating supplies.
We will learn how to utilize the resources we find on these other worlds, starting with finding water ice and purifying it to drinkable water.
And refining that into hydrogen for fuel and oxygen to breathe.
We will establish fission power plants on the surface of the moon, capable of supporting a growing community of efforts.
And we will expand the logistics supply chain to enable commercial and international partners
to resupply and refuel deep space outposts.
None of this is simple or easy. Nothing in our history ever has been.
The Eagle has landed. We got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
This kind of continuous lunar presence is a natural extension of all that we've learned in low Earth orbit. And what we will accomplish there will ensure the monumental missions to Mars are within reach. As we ready the launch of the first Artemis mission, and as commercial companies ready their lunar landers for the first private payload deliveries, we have already begun to take the next step.
Hello. Welcome to 2022's version of NASA's Lunabotics competition. My name's Kurt Lloyd. I'm a NASA engineer. I'll be hosting the Lunabotics competition and narrating this week. I am standing in the middle of our Lunabotics robo pit, and you can't see the whole thing on camera. You can only see about a half of it, but there's a lot of activity going on. and a lot of noise in here, so I hope you can hear me okay. I want to thank all of the people that are watching online. And for those who want to tell their friends and family back home how they can watch the live stream, just point them to nasa.gov/Lunabotics. NASA.gov/Lunabotics is our main Lunabotics webpage. And from that page, you can click right onto today's live stream, and then there'll be another link, a different URL for tomorrow's live stream. But they can find that on the same website, nasa.gov/Lunabotics, right there on the screen. Now, all around me are nearly 20 teams of college students. If you're not familiar with our competition, nearly 20 teams of college students and university students who have converged. They've been working all year long at their universities to create digging robots, mining robots. And the purpose of Lunabotics is to present a robot that is capable of mining or digging on the moon. These are robots that are pretending they're on the moon, and they're going to dig in this crushed volcanic rock that we have in our arena. And this crushed volcanic rock looks and acts a lot like moon dirt. But under the crushed volcanic rock, we have hidden gravel, and that is actually acting like the icy regolith or frozen water underneath the surface. That's really what these robots are here to dig and collect and deposit. So in just a few moments, the teams are going to start competing in our arena. But you can see around me the frenzy and the excitement that's going on in the robo-pits. And these teams are going to be in the robo-pits here all day, working on their robots, doing some last-minute tweaks, some last-minute tests. You can see pieces of robots sitting on the tables, pieces of robots being carried around the room. Oh, I need to get out of the way. I don't want to get in the way. The last thing I want to do is get in the way of any of these competing teams. So it's going to be, I mentioned that we had nearly 20 teams here today. That's only half of our field. If you were paying attention, if you had the chance to watch earlier in the week, Monday and Tuesday, we had another nearly 20 teams in this room that competed. And if you want to go back and watch some of those competitions, you can watch the Monday and Tuesday live streams by going to nasa.gov/Lunabotics, and the links are there for you to watch Mondays and Tuesdays live streams. So that's what's happening in the RoboPit area. Now, let's go to a live camera view from our Artemis Arena, where the teams are momentarily, in just a few minutes, going to be bringing in their robots to perform the first run of our very first two teams today. So what you're seeing on the screen right now is our brand new Artemis Arena, indoor Artemis Arena. If you're familiar with this competition, and if you've paid attention in any of our prior years that we've run this competition, in the past years, our Artemis Arena was actually outdoors and under a tent in a non-permanent facility. And anytime there was a strong storm or any lightning in the area, it actually caused an interruption in our competition. And so we've spent some time and energy and money in order to create a permanent indoor Artemis Arena in a permanent facility. And so um, we have some live cameras showing different angles, different views of our Artemis Arena. And if we can switch to just the overhead camera view for a moment, I will describe the competition, the actual event that these robots are going to be competing in. On the right-hand side of the screen, the robots will be brought in to the Artemis Arena by their student team members, and our Artemis Arena judges will help those student team members load their robots into the arena. And the arena, you can see, it is mostly a gray colored dust, and that gray colored dust is a simulant of lunar soil. It's actually crushed volcanic rock that we got from Arizona. And this crushed volcanic rock has some very unique properties. It is not easy to drive on, nor is it easy to dig in. And that's exactly what we're asking these robots to do in our Artemis Arena. The crushed volcanic rock has some fairly unique properties compared to, say, beach sand that you would find at a typical beach. Beach sand has been slowly eroded and worn over time, and so each particle of beach sand is very smooth and very round. That is not the case for this crushed volcanic rock, and it is not the case for lunar soil. Lunar soil is broken up over many, many, many years and many, many millennia um, due to micrometeorites and things like that, impacts from asteroids and meteors, and so the fine dust that covers the surface of the moon has been broken up and broken up and rebroken up over so many years that it is a very, very fine powder. And because there's no air on the moon, there's no water that's running, lakes, streams, rivers, that sort of thing on the moon, this powder never gets worn like beach sand gets worn. It never gets rounded off, it never gets smoothed. And so these particles are very jagged when they're broken up, and they stay jagged forever. And so that causes this powder, this lunar soil, to have some very unique mechanical properties, and it reacts differently to, say, beach sand. And so what we see on the lunar surface is the top few inches is very light and fluffy, and if you're not careful, you can sink into it, especially if you jostle it or wiggle it around. You can sink into it. Underneath the top few inches, though, the soil becomes very compact and almost solid, almost like a hard surface. And so it's the same particles, but they're acting differently based on their height from the top of the surface. And so the teams that are competing in this competition this week, they have to create robots that are able to drive on top of this crushed volcanic rock and not sink into it and not get stuck. And so the competition involves starting the robots on the right-hand side of the arena that you're seeing here. We have split our arena into two courses, two runs. We have Arena A on the bottom side of the screen. We have Arena B on the top side of the screen. We're going to run two teams robots simultaneously. We'll put one robot on the A side and one robot on the B side. The robots will start on the far right side of the screen, which we are pretending is the lunar lander that just dropped these robots off onto the surface of the moon. The teams will then either manually drive their robot, or they will use an autonomous mode if they have designed the robot to be autonomous. And the first thing that the robots need to do is they need to get from the right-hand side of the screen all the way over to the left-hand side of the screen. The left-hand side of the screen is our excavation area or our digging area. But between the lander on the right and the excavation area on the left, our judges have created an obstacle course, so to speak. They've put some large rocks, and they have created some shallow holes which simulate craters on the moon. And now that we see a lower camera view, they have actually created these berms or hills. They're like linear hills right in the middle of the obstacle course. Now, I do call this an obstacle course, but some teams may have created their robots in a manner. They may have designed their robots in such a way that they can climb right over these rocks. Some of the robots might be able to drive right through the crater and not have any issues. Some of the robots might be able to drive right over these berms and not have any issues. Some of the robots were not designed in such a way. And this is a really interesting point because some of our robots are in our competition this week are bigger, heavier. Some of our robots in our competition this week are smaller and lighter. And it's not an obvious outcome that a bigger, tougher robot is automatically going to win this competition, because this competition has some complex scoring going on. Teams are not only scored on their digging, their excavation abilities, they're also scored on how lightweight is your robot. They're also scored on how little power does your robot use. If you use less power, you actually get a better score in that category. These robots are also scored on elements such as how much communication back home, back to the control center, does your robot use in order to operate. If you use less communication and the robot is doing more self decision making and self autonomy, you will actually get a bonus in your scoring regimen. But I should finish the mission. So once the robot gets all the way down to the excavation area, they have to cross that orange line that the judges have drawn in our crushed volcanic rock. Once their digging implement has crossed that orange line, they are allowed to dig in that area. And it's not just a matter of digging up this crushed volcanic rock, the gray dirt that you see on the screen. The task for these robots is to get underneath the crushed volcanic rock and to pull up the rocks, the gravel that our judges have hidden beneath the surface. And those rocks or gravel simulate an icy soil or just solid ice chunks that are hidden beneath the surface. Once the robots pull up these ice chunks, which are simulated using gravel, then they have to go all the way back to the lander. So they have to cross the obstacle course one more time. They have to go all the way back to the lander, and they have to deposit these rocks onto a screen mesh, which is which you can see as these rectangle-shaped boxes or meshes on the screen there. Once the robots place their gravel or rocks onto that mesh, the judges will weigh on a scale. They'll weigh the mass of those rocks, and the teams will get a score a higher score based on more rocks that they bring back. And robots are allowed to go back and forth as many times as they want to or need to in order to bring back as many of the buried gravel that they can. they will only have 15 minutes to do all this work. So this is a pretty challenging event. There's a lot of moving parts. There's a lot of things going on. Robots have to, not sink in the soil. They have to get past the obstacle course. They have to dig, but they don't just have to dig. They have to dig deep. They have to pull up some certain elements that we've hidden under the surface and bring those elements back and deposit them. And it's a lot going on. Some teams are going to be manually stick driving their robots throughout their entire runs. Other teams are trying to gain additional autonomy points by adding sensors to their robots and transmitters and receivers and other types of like 3D environmental sensors and software, because you can't do autonomy you can't just add a bunch of sensors in your robot and expect it to make its decisions on its own. It requires a computer that is capable of handling autonomy, and it requires not a trivial amount of software running on board your robot in order to take in all the sensor data and to make sense of it and to make decisions out of it and then to command the robot appropriately. There's a lot of moving parts there, especially for the teams that decide to try the autonomy. So that is I was going to say a high-level summary, but that that was actually pretty detailed. That is what each of the teams that are competing here this week are tasked to do. And each team is going to get 2 tries. They're going to get 2 15-minute runs in our arena between today and tomorrow. We've already gone through half of our field on Monday and Tuesday, and we're able to give all those teams 2 runs in our arena. And today and tomorrow, we will be giving the second group of our entire field 2 runs in our arena today and tomorrow. So that is a quick overview of our competition. Don't go anywhere because our first 2 teams are they should be getting ready and they should be coming into the arena in just the next few minutes. And it looks to me like my computer is telling me that the first 2 teams are going to be Temple University and College of DuPage. Chris? All right, so I'm going to go ahead and read off what my screen says, and then but I will run into the RoboPits after I say this out loud, and I will make sure that I'm not lying to you, and I'll come back with a correction if I'm wrong. But my screen is telling me that Temple and College of DuPage are going to be running first, and then after that, the University of Nebraska-Lincoln and the University of North Dakota will be running after that, and then our third run to the just all by themselves. Now, caveat is highly fluid, ever changing, constantly changing, and so we will continue to audibly go over our current schedule so that the folks that are watching from home are able to stay informed as to our current schedule. It's all right, we have another screen that may actually have the correct information. We have a computer screen that's telling us North Dakota State University and the University of Maine are going to be going first. And then after that will be Temple and DuPage. After that will be Sonoma State and University of North Dakota. After that will be University of North Florida and University of Virginia. Do stand by and be prepared for updates to that schedule, and just be aware that it's a constantly changing schedule, and we will do our best to keep those of you informed as to changes on our schedule who are watching online today. Thank you all for watching online, and if you want to share the URL on social media with friends or family, feel free to do that. We would love for a lot of people to be aware that we're live streaming today. So you feel free to share the URL right from youtube.com. You can also share the URL nasa.gov/Lunabotics, which has a link right at the top of the page, basically, to the current live stream, and also link to Mondays and Tuesdays live stream for anybody who might be interested in going back and watching replays of those days. So keep watching. I know the teams are frantically getting ready to get their robots into the arena. So don't go anywhere, because you don't want to miss the very first run of this group of college teams who have come all the way to Florida after working all year long on their robots at their school. So don't go anywhere. This is NASA Lunabotics 2022 competition, live from the Kennedy Space Center Visitor Complex in sunny Central Florida. All right, it looks like Temple University and College of DuPage are going to be going first. So don't go anywhere, stand by. We should see those robots start coming into the arena very soon. All right, we're looking at a live camera view from our Artemis Arena. And what you're seeing is the College of DuPage bringing in their robot into the far side of the arena, which is labeled Arena B. And we had just passed the Temple students in the hallway, so they're in the room, and their robot will be coming in momentarily. As we wait for the Temple students to bring their robot into the arena, we can start looking at the DuPage robot. It has four pretty good-sized wheels. They're a lot bigger than a lot of other teams, and I think that may give them an advantage. We'll have to see if those wheels do really well in this crushed volcanic rock. One fun thing about the wheels, you can see how brightly colored they are. Most of the wheels, all the outside part of the wheels anyway, with the treads sticking out, and the sidewalls are all 3D printed. So it's that's partly why you're seeing the strange colors there, is because this plastic that you buy for your 3D printer comes in all kinds of colors. And so these are four 3D printed wheels, and they've got a system where one motor is being split and driving the two wheels on the right hand side of the robot, and then a second motor is splitting in order to drive the wheels on the left side of the robot. And one interesting thing I noticed about this robot, we'll see it later once the robot turns around. The front of the robot is to the upper left of the screen right now. You can see a black arrow on the left side of this robot, which is telling the judges which direction is the front of the robot. And once we can see the front of the robot after it starts moving and turns around, you'll see that there's an auger, like a spiral digging auger on the front of this robot. And so that whole box, that whole rectangular box that's on top of the DuPage robot, it will rotate so that it becomes vertical. And then the auger, I assume, will start spinning. The whole auger actually plunges downward while it's digging. And what you'll see on a lot of the robots in this competition is they will dig, using whatever mechanism they decide to use, and they will move what they've dug into another part of the robot for storage, and then for transferring from that part of the robot off of the robot onto the lander. Well, the DuPage robot stores the material in its auger box and then drives back the lander, and then they just they just point their auger input or the auger output towards the lander, and they run their auger backwards in order to unload what they have dug up. So it really simplifies their design of the robot. Will it be an advantage, or will it end up being a disadvantage? Only time will tell. We will see how both of these robots perform. So on the right side of the screen, you're getting a good look at the Temple University robot. Temple robot also has 4 wheels. And notice the difference in tread between the DuPage robot on the left and the Temple robot on the right. The Temple robot has treads. You can see a zigzag pattern there on the wheels, but the treads on the Temple robot are thin, I guess is the right word. They don't stick out from the wheel surface very much. And the tread on the DuPage robot are pretty tall. They stick out from the surface of the wheel quite a bit. So it's going to be interesting to see these robots run simultaneously and see if one of them is able to drive across this surface without sinking in better than the other one. And since both of these robots have 4 wheels that don't actually turn, let me spend a minute explaining how these robots will turn. A lot of our teams do this. They mount their 4 wheels, or however many wheels they decide to put on the robot. They mount them onto an axle that doesn't actually turn. Like the front wheels of your car actually turn to the right to make the car go right, and they turn to the left to make the car go left. These wheels on most of these robots you're going to see today and tomorrow don't actually turn. So these robots are more like a tank. We call it tank steering, or we'll call it skid steering a lot. And in order for these robots to turn right, for example, they just they command both of their right hand wheels to go backwards, while commanding both of their left hand wheels to go forwards. And if you can imagine the right wheels going backwards and the left wheels going forwards, that's going to make the robot spin to the right or in the clockwise direction. And a lot of our teams pick this sort of mobility steering design. Steering's not the right word, but the turning design, which is skid steering or tank steering. I suspect they choose it to simplify and create less moving parts for the robot. It also gives the robots the ability to turn in place. You know, your car can't just spin around in place on a dime, but these robots can literally spin around in place on a dime. So in this particular space that they have to operate in, that can be a real advantage. The downside to turning in place and skid steering is your wheels actually have to slide sideways. They have to slide left and right. Imagine the robot on the right is spinning clockwise. It's spinning to the right. Well, that means the front wheels have to slide across to the right on this fluffy soil, and it means the rear wheels have to slide to the left, diagonal to the wheels' normal direction of travel. Hopefully that makes sense. And this ability to slide can, if the wheels are designed, properly, and they're designed so that they can slide while turning, it can be a real advantage. But in this soil, I mentioned earlier that the top of the soil is light and fluffy, and when your robot is trying to slide sideways on top of this light and fluffy soil, sometimes it can dig in. So sometimes robots can dig in and hit that harder material beneath the light fluffy stuff and get a little bit stuck. So there's I'm saying a lot of pros and cons, but I want to be clear that there's not one obvious correct solution. There's not one obvious incorrect solution. All of these teams they have done their research. They've maybe even tried different techniques, tried different wheels, and tried different digging mechanisms and tried different dumping mechanisms, and have decided based on data um, which is the proper design for their robot. And so um, we're going to see nearly 20 different robot designs, and we're going to be able to see what works best and what doesn't work best. Something that works really great might depend on the weight of the robot that you put on that wheel. So you may have picked a really great wheel design, but only works really great if the robot is really light, and then another perfect wheel design might only work for like a really heavy robot. I'm just babbling because I'm not I'm not a mechanical engineer, so I really don't know the details about the all the different trade-offs when designing wheels. I'm just trying to give the audience some simple examples of the decisions that these students need to make when designing their robots, and none of them are necessarily the absolute wrong decision. But when you combine certain decisions they make here and certain decisions they make there, sometimes combinations of decisions can end up working against a team. Sometimes combinations can work for a team. There's so many variables in a competition like this. It is it's pretty intense. This is a pretty intense design competition for these students. A lot of schools will make this a senior design grade for these students, and they spend literally all year, because we release our rules usually in the late summer, and so it's in the early fall that the students first get a chance to look at our rules for the year, and then they spend basically all year going through the engineering design process, the systems engineering process, to very carefully and very procedurally design, build, test, fix, or build again, test again, before they eventually, at the very, very end of their senior year, end up being able to travel to Florida and run their robots in our simulated lunar soil bin. Now, the students are given some time to activate their robots, and I should mention that some of the students from each of these teams are in the control room down the hall, where they are unable to see the robots with their eyes. Um, there is one camera view that we supply them that they are allowed to use if they want to view our camera view of their robot. If they choose to use our NASA provided camera view, there is a little bit of a point penalty for choosing that. We see a little bit of movement from the DuPage robot just there. It rotated its auger down a little bit. And what's happening now is the students in the arena are. Let me finish my thought though. The students are allowed to use a NASA provided video feed that is kind of limited. It is kind of an overhead view that is kind of, we're pretending that it's the lander's view of the robot, and so they can the teams can only see their robot from that angle. If they want to see, if they want to put onboard cameras on board the robot, they're welcome to do that. But keep in mind, as I said earlier, the more bandwidth that the robot sends back to the control room, that can actually be a disadvantage points-wise. So there's lots of variables, lots of pros and cons to all the choices, all the decisions that these teams make. I love that the DuPage robot rotated its auger all the way back so that it's pointing up. An auger needs to point down when it's digging, but the reason it might want to point up is, I suspect, so that it can reach up into above the lander's mesh in order to run its auger backwards and dump its load onto that lander's mesh screen. So these students who are activating and checking out their robots in the arena are communicating using a radio back to their fellow students, their fellow teammates that are in another room down the hall, which is our control room. And in that control room, the students are bringing in their laptops. They're maybe bringing in some monitors, or maybe bringing in some joysticks or game pads or whatever they're using to control their robot and to monitor their robot. And we have judges in the control room that are monitoring that activity and making sure that everything's working good. And so these students are communicating with their fellow teammates back in the control center and verifying that the data is looking good, verifying that they're able to command the robot. And it looks like the Temple students have left the arena, and it looks like the DuPage students are leaving the arena now. So what's going to happen once the students leave the arena? The students in the control room, which are not in this room and don't have visibility other than some camera views, they will be controlling these robots, or they will be hitting a start button in order to start some sort of an automation routine on these robots. And as soon as our judges put some finishing touches on the arena, and as soon as they communicate that the arena is ready to go, and as soon as the judge who's monitoring the control room and calls on the radio that the students in the control room are ready to go, they will start a 15-minute timer, and these robots will have 15 minutes to perform their mission. So that should happen within just a few moments. So don't go anywhere. You're about to see College of DuPage on the left and Temple University on the right performed their first of 2 official competition runs this week here at the NASA Lunabotics 2022 competition. So you can see both robots are moving. You can see the 15-minute timer at the top of the screen. DuPage on the left, Temple on the right. And they're kind of matching each other's moves, aren't they? They're both doing 3-point turns. Actually, DuPage is spinning beautifully in place. And Temple's doing a 3-point turn. So both of these teams are trying to get their robots pointed in the right direction. So I should mention, we don't have any visibility or knowledge as to whether these teams are stick driving these robots or whether there's some automation routines going on. So we're just going to presume, based on the movement of these robots, whether they're being manually driven. I can see the Temple robot making some progress. So now the Temple robot's on the bottom, and the DuPage robot is at the top. And you can see the tracks that the Temple robot is leaving. It is definitely making some progress on that rotation. It has finally gotten past that rock, and it's turning. Now the Temple robot on the right needs to get past that berm. I don't know if it can get over it. DuPage has gotten past the berm, and they have just gotten over the line into the digging area. So now DuPage is able to dig in this area, anywhere in this area. So they can choose any spot that they want to dig. And it looks like they're going to turn around first. That's possibly a wise move. They need to turn around to dump, so might as well do it now, and then they can just run straight back to the starting point. Okay, Temple on the right, they did get past the first rock. They got past the berm, but now they're pointing right at another rock. And so they're going to have to do another 3-point turn, a 5-point turn, or 7-point turn, however many points it takes in order to get their robot pointed. One more turn, and they'll be pointed directly towards the digging area. Okay, DuPage has looks like they've made contact with their rotating digger. And you can see the motor disappearing in the center of their box there. So that motor is turning their auger, but their whole digging system is actually being plunged down into the ground. So they're making good progress on their digging already, and we're only 3 minutes into this 15-minute run. On the right, Temple has started digging with their rotating conveyor belt driven bucket ladder system. It's almost like a trencher because it's actually digging toward the robot. But you can see, boy, it's really digging in hard and almost lifting the front of the robot up off of the ground when it really hits the hard stuff. Once you get more than a few inches down, this crushed volcanic rock gets very hard, very compact, and it can be pretty hard to dig in. So you can see the front of the DuPage robot on the left is completely lifted up off the surface. So it's pushing down at a faster rate than it's digging, but that's probably fine. I can't think that of any problems that would cause, unless the robot changes its position enough that it ends up binding the the temple robot. We've got some loose belts there, a loose conveyor that may be a problem for Temple. Let's see how they handle that. And I should mention that the students, if the students are watching the NASA provided lander camera view, they're basically seeing kind of the opposite angle that we're looking at on our screen. We have access to a lot more cameras around the arena. The students are only given access to the lander cam, which is at the opposite side of the arena from where we are right now. So Temple is raising their digging mechanism. DuPage has raised their auger and rotated it back vertical. Now they're heading back to the lander. They got to cross that obstacle area. Oh, Temple's digging again. So whatever that buckling or loosening was of their belt has recovered. I don't know what kind of springs they have in their system to allow for some compression there. I was afraid something was broken terribly, so I'm really happy to see that Temple is not. So while we see Temple dig, we can also see DuPage heading back to to deposit what they have dug. So their robot's a little heavier now than it was before, assuming that it's full of this crushed volcanic rock and the gravel, which is actually the scoring material. We're going to get a nice tight view. Oh, look at that! They're actually extending before they offload. That is an interesting design choice. All right, let's watch them offload and see what comes out of this auger. Part of me wonders if there's some automation going on with the DuPage robot. Because if I was stick driving this robot, I probably wouldn't have extended it that far. Okay, they're bringing it back. There may be they may be having a little bit of communication weirdness going on with their commands to the robot. It's hard to tell. So I should mention, if any of these teams do try some automation, there's lots of flexibility there. They can automate individual tasks. Like they can automate the crossing the obstacle field, and they'll get a certain number of autonomy points for just crossing the obstacle field autonomously. Or they can automate just their very first dig pass, their very first attempt at digging, and they'll get a certain number of autonomy points for that. And then they can automate just the offloading of the material at the lander, and they'll get a certain number of points for that. But teams that do an entire run where they do multiple back and forth passes, they will get the maximum amount of autonomy points. Let's go back to Temple, right? Temple, who have raised up their digging system, where we're about in the middle of this run. We're almost 8 minutes in, 7 minutes remaining, and so Temple has decided to not take any chances, not wait till the last second. They're going to try and get their robot back, and it looks like it's having a little bit of trouble steering. So they need to go to the left or rotate counterclockwise. So the right wheels need to move faster than the left wheels. But if there's a little, they're turning a little bit there. But if there's a little bit of slip in the soil, or this robot is obviously heavier now than it was earlier. All right, they're finally making a little bit of progress turning. Temple is at the bottom of the screen, and I'm not sure what's going on with that DuPage robot. I wonder if they're having trouble running their auger backwards. This is something that can happen in this competition. The rocks and the gravel, which is the point bearing material, and the crushed volcanic rock can really do a number on your mechanical components. It can bind, it can get into cracks and crevices. It can bind things up and keep them from working properly. This Temple robot at the bottom of the screen is is trying to drive over that rock for some reason. That kind of tells me that this may be a fully autonomous run for this Temple team. You can see some sensors at the front of the robot that are, oh no, those may be motors. I don't know if those are sensors or motors. I'll have to look at this robot later. But the DuPage robot did not look like it was able to offload anything. And I don't know if the students gave up and just went back to the digging area for fun, or if they have a plan for unloading their haul. They may be just using the time that we have left, which is only 4.5 minutes, to just get a little bit more runtime on their digging mechanism. This is an exciting run for our first run of the day, because both of these robots have made really, really amazing progress, and they are so close to getting points. If they can just offload some of these gravel rocks onto the wire mesh at the far right of the screen. So the Temple robot, you can see the wheels moving from this angle. You can see all 4 wheels of this Temple robot are moving, and yet the robot does not appear to be moving. What I think is happening is I think their digger, which is to the lower left of this robot, I think their digger's dragging the ground a little bit, which is keeping the robot from making forward progress. I could be wrong. But what happens if they get their wheels, if their wheels spin away too much of the crushed volcanic rock beneath them, they will end up becoming high-centered, and all the wheels will basically be floating in midair and not doing any productive work anymore. These wheels are still doing productive work. It's just that they're kind of stuck between a rock and a hard place. Pardon the pun. So again, Temple is at the bottom of the screen. DuPage is at the top of the screen. DuPage their front wheels were just off the ground again. We're less than 3 minutes, 3 minutes left in this 15-minute run for both of these teams. It's going to be sad. It's going to be sad if we run out of time and neither team has deposited any of the gravel onto the lander. But both of these teams should feel really proud. They should be really happy with the progress that they've made. This is a really, really tough challenge, and I'm impressed with both of these robots. Okay, we see Temple lowering. We see Temple lowering their digging mechanism. I wonder if that's going to help them, or if it's too late, if they've already dug in too far. Okay, they're being a little bit more aggressive now, which is appropriate. Obviously, they're stick driving this robot. DuPage at the top of the screen is coming back. Okay, we got 2 minutes left. What are the odds that this DuPage robot is going to come back in the last 2 minutes and deposit some rocks onto the lander? Oh, look at which Temple. Temple got out of that hole. Now don't go back into it. Let's turn to the right a little bit more before you. There you go. Look at that. Okay. Yep. If they can turn to the right a little bit more, they will be lined up. Okay. We have a minute and a half left. What is going to happen with these teams? Temple at the bottom of the screen, DuPage at the top of the screen. So DuPage on the left, Temple on the right. This is so exciting. It looks like, unless something weird happens, it looks like Temple is going to be able to unload something in the last minute of this 15-minute run. So let's watch them. Oh, it seems to be, it's trying to move. Oh man, oh no, something may be bound up. Something may be bound up on both of these robots. Oh yeah, DuPage, look at that. They're finally unloading. And Temple is trying. You can see their belt trying to move. Something may be bound up. Okay, and you can see some. So the rocks are lighter colored than the gray soil. The rocks are almost white. The gravel is almost white, and I'm pretty sure I see some gravel there on DuPage's lander. So congratulations, DuPage! In the last minute of the run, finally got their auger to spin backwards and unload the material that they had collected earlier. Meanwhile, of the screen, they are so stinking close. I hate to see a team get this close and not be able to get any points out of this run. The good news is, as we run out of time, that both of these teams will get time to go back and look at the robots, perform any modifications that may need to be performed, and any fixes that may need to be performed if anything broke. And they'll be able to come back tomorrow for a second of 2 official competition runs in this 2022 edition of NASA Lunabotics Collegiate Robotic Mining Competition. Don't go anywhere. The teams that are going to be coming up next are University of Nebraska-Lincoln and University of North. And then after them, we will see University of North Florida and the University of Virginia, plus all the rest of our field will be lining up and will be scheduled after that. So don't go anywhere. You're watching Lunabotics 2022. So I'm being told that when the camera was not on the DuPage robot earlier, it actually was able to unload some of their crushed volcanic rock and maybe even some gravel onto the lander. We just missed it because we were at that moment focused so much on the Temple robot and the struggles that they were having. So yeah, that's. we're trying our best to watch all of our cameras and not miss anything, but occasionally we miss something like that. So great job, both of these robots, both of these teams. I can't wait to see both of their second runs. This is great stuff.
Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind, the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there is no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned, and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach: pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the Moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the Moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit, and once again to sling the spacecraft around the Moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released, and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our Moon and prove that together we are ready to go beyond.
We are looking at the RoboPits at the NASA's 2022 Lunabotics competition, where we have 20-some teams competing today and tomorrow, and we had, or nearly 20 teams competing today and tomorrow, and we had nearly 20 more teams competing Monday and Tuesday. These are collegiate teams working on their robots, and these robots are intended to dig down deep on the Moon, pull up ice that's buried deep under the surface, and bring it back to the lander. earlier in our run that had DuPage and Temple running simultaneously, the Temple robot actually slammed into a rock several times on its way back to the lander. And it's funny because I assumed that that was not on purpose, but I just passed the students in the hallway and I overheard them saying, "Yes, that was on purpose. We were trying to knock loose our whatever our belt or whatever." So it's I love finding out behind the scenes information like that. If we go back to our arena cameras, we can see that our next two teams are starting to get ready for their runs. Our next two teams that should be running in the next few minutes are going to be University of Nebraska-Lincoln and the University of North Dakota. And you can see North Dakota on the upper left side of the screen bringing in their robot right now, and Nebraska-Lincoln on the lower right side of the screen have already set their robot into the arena. The North Dakota robot, which was just set onto the surface by the students, has a series of scoops or buckets that are attached to a rotating mechanism, a belt or chains or some sort of mechanism that rotates them around. Basically a bucket ladder system that can rotate so that it's more upright and it can plunge downward beneath the surface. The Nebraska-Lincoln robot, I don't think I've had a chance to look at this robot close up. Obviously, it has tracks instead of wheels, whereas the North Dakota robot has 4 wheels. One thing I did notice about the North Dakota robot earlier when I was walking through the pits is that this North Dakota robot, which is in the upper left, has a lot of carbon fiber composite materials. All the parts that are basically black colored on the camera are pretty much carbon fiber composite parts, which is a very strong material, but also lightweight when compared to the same strength of metal components. So the wheels, at least the outside, the tread and sidewall portion of the wheels are all carbon fiber composite. The buckets are all carbon fiber composite. Part of a large part of the onboard hopper that holds the material that has been collected by the buckets, fiber composite panels. And using materials like that, high-tech space age materials like that, helps reduce the weight of your robot, assuming that they can still do the work and they're as strong as other optional materials that could do the same work but would be heavier. So they get teams that choose materials like that get a little bit of a points advantage based on the weight of the robot, the strength of the robot versus the weight. You can see the North Dakota students have installed a large black and white, it's like a barcode. It's a digital pattern that an onboard camera on the robot can see, and most of the time, I can only presume what the students are using that for, but most of the time, a camera on board a robot and a fixed barcode like that on a facility are used for the robot to calculate exactly where it is located in 3D space. So if the robot drives 2 meters away from the lander and then looks back at that barcode, it can do some trigonometry calculations really quickly and calculate, yep, 2 meters is exactly how far I am for the lander. Not only can they calculate distance by using a barcode like that, they can calculate angles. So if the robot is, 2 degrees to, clockwise, clocked, to the right or left, those same trigonometric functions can be used to calculate the angle that the robot is away from the lander. So between distance and angle, you can basically calculate where your robot is in 3D space. Both of these robots have moved a little bit since the students have placed them into the arena. And what's probably going on there is they're talking on the radio to their fellow teammates in the control room, telling them that the robot's been powered on. Do you see data? Okay, try a quick command, and then they'll try a quick command and see if the robot responds. So that's probably what you're seeing there. So the fact that both of these robots moved a little bit sort of implies that everything's working. Commands and data probably working fine, and so these students are probably happy with their robot checkout, and we'll probably see them exit the arena, and then the judges will put the finishing touches on the arena before they allow the run to start. So in just a few moments, we should be able to see a 15-minute run, run one of 2 official competition runs for all teams this week, with Nebraska-Lincoln on the right and North Dakota, University of North Dakota on the left. Might notice that for the first run of all of these teams, the students appear to be placing their robots facing to the left, facing to the upper left, facing to the side of our arena, and that's not random. That's not the student's choice. The judging team is basically requiring the students to place their robots in that orientation in order to perform their first of 2 runs. We're trying to, this is in an effort to add another level of complexity to the mission. The robots are not facing in the direction that they necessarily need to be facing in order to get down to the digging site. And so there's so many little subtle complexities about this competition that when you add them all up, it makes it a really, really difficult competition for these students and for these robots. And obviously, we have started. So the tracked robot, which is Nebraska-Lincoln, immediately backing up and turning. The North Dakota robot, one of its wheels started spinning right off the bat, but not all of its wheels were spinning. So that was a little bit of a weird start. But it looks like all the wheels appear to be operating nominally. Now the Nebraska-Lincoln robot, now that it's turned a little bit, we can see a little bit more of their design. They've got a really good-sized auger on the front of their robot. they've got to get turned around so that they avoid that rock, though. So Nebraska Lincoln is now at the bottom of the screen, and University of North Dakota is at the top of the screen. Now, North Dakota just deployed their digging mechanism, or they just moved it away from its starting position. And it looks like the North Dakota robot is having an easier time turning to the right than it is turning to the left. And that's almost the same. I could almost say the same thing about the Nebraska Lincoln robot. It seems like it's turning right kind of by default. It looks like its right track seems to be maybe hanging up every once in a while and making them have trouble turning left. Yep, their right track looks like it gets stuck at the same exact spot every time. And it's pretty obvious from the overhead view because we can see where the right track is dirty. Whoa, there was a big move there from the North Dakota robot, but they got their robot pointing in the right direction with that move. Nebraska Lincoln, meanwhile, at the bottom of the screen, still appears to have some trouble turning left. Their right track seems to be stopping at the exact same, it just seems to be hanging up somewhere at the exact same spot because the top of their track has a clean spot that is just never actually turned beyond. See how it got stuck there? All right. University of North Dakota has made it all the way into the digging area. They had a little bit of mobility issues, a little bit of turning issues, but they got past them. You can see their bucket ladder system spin there for a second. It started out going in the opposite direction. I'm not sure what that was about, but now it's spinning in the dig direction, and boy, it's taking out some big scoopfuls. Keep in mind that the students cannot see this amazing view. They can't see this amazing angle that we're looking at. So they may not have the same information that we have. They may not know. They may not realize whether their buckets are deep enough or too shallow. But now it looks like things are starting to settle in with them. They found a groove. Now, I suspect that this digging mechanism, this rotating bucket ladder system, is able to plunge downward in order to go beneath the surface. So let's keep watching the North Dakota robot, and while the Nebraska Lincoln robots be still having the same issues getting past that rock and getting the robot turned in the proper direction. Let's see if this North Dakota robot can lower their digging system in order to get more scoopfuls. I presume that's what the students are. Actually, I made the mistake of assuming that the students were controlling this robot, but because of their barcode that they installed at the lander, it's completely possible that this robot is running autonomously. Only a few people in the building know whether this robot is running autonomously or not. It's the students in the control room and the judge in the control room. So the rest of us just have to watch and try and look for clues and hints about whether the robot is being manually driven or being driven autonomously. I suspect it's manually driven. It's completely possible for teams to install barcodes like that and to use the sensors on the robot just to just to give more information back to the students in the control room who are controlling the robot, to give more data and to give more visibility into those students who are controlling the robot. So it's possible you can have a lot of sensors and transmitters and things like that, and still not actually try the autonomy. So the North Dakota robot, it seems like it's rotating bucket ladder system. Seems like it was binding up a little bit just there. When we saw it move, it seemed like it was pulling a little bit in a weird direction. So something maybe right there, something maybe hitting something and pulling it in a weird direction. Yeah, right there. So let's see what the students do for troubleshooting that problem. I suspect one of their buckets is underneath hitting the robot. Let's check on the Nebraska Lincoln robot. Okay, it's pointed. I was gonna say better, but I guess it's probably pointed in the same direction that it has been earlier. And it does appear to have stopped moving. I hope they didn't break something. This is actually a pretty good angle to see kind of a side view of the University of North Dakota robot as it digs. You can kind of see the angle of their digging system. Right there, I think that's the angle that it probably is intended for digging. You can see they spun their wheels there, possibly trying to grab a scoopful. You just saw it try and move there, and it does appear to be bound up still, even at this high angle, it does seem like it's bound and hitting something. Well, even if the North Dakota digger is kind of stuck, they were able to throw several scoopfuls into their onboard hopper earlier before it did get stuck. Oh, there it just got free for just a little bit, and now it appears that the next bucket has come around and gotten stuck on the same element. But what I was about to say was that since they had some scoops that got deposited earlier into their onboard hopper, I wonder if they do have an opportunity to go back to the lander and at least deposit what they have dug so far. Although I will say, and the students probably are fully aware of this, that they haven't gotten very deep. Those initial scoops that are on board were not very deep, and so the likelihood that there's any gravel or simulated ice in their onboard hopper is probably pretty slim. We're 9.5 minutes into a 15-minute run for these two teams, and keep in mind, there they go. North Dakota's heading back to the lander, it looks like. Keep in mind that these two teams, this is just their first run of 2 official competition runs. So anything that goes wrong in their first run, the teams can learn from. The students can make corrections. They can make fixes. They can, go back through their inspection before they come back out to do their second run. And okay, it looks like Nebraska Lincoln on the right is going ahead and getting a little bit of runtime in on their digger since they were unable to get out of that spot. Let's go ahead and not just waste this time. We're in the bin. We're in the arena. Let's go ahead and test out our system. I guess University of North Dakota had a little bit of an alignment issue, and so they're going back for a better alignment. Although they're back to the phase where they don't seem to have very fine control of their pointing angle, and that is a crater, folks. The North Dakota robot has driven right into a fairly deep crater, but look at that. This robot was strong enough, it had all four wheels spinning, and was able to get itself out. So that's a good, strong robot. It's just that I think they might be having some control issues. Now, Nebraska Lincoln at the bottom of the screen appear to be making some reasonable progress with their digging. Now North Dakota. It's hard to tell from this vantage point whether North Dakota is having control issues or whether they're actually having fun and playing. They do need to be careful not to break their robot any further so that they can have an opportunity to come back for a second run. And now they may be digging themselves into a hole. Nebraska Lincoln, with only a few minutes left in this run, is doing some practice digging, and that'll give them some information that they'll be able to use in their second official competition run. Looks like they're actually raising and lowering their auger. Their auger is very fast when it spins. Did they pull up anything? I mean, they definitely made a hole, Nebraska Lincoln, on the lower side. Did they actually pull up anything into their onboard hopper? I'm not sure. I may have been looking at something else when it happened, but I didn't notice. Oh yeah, there might be I can kind of see some gray material. Yeah. Looks like they did get some. So you can see they've got an onboard kind of flipper that, oh, look at that. Oh no, it fell to the ground. Did everybody see that rock fall to the ground? That wouldn't have counted anyway, to be fair. Since they're not digging in the approved digging area, even if they had dumped a rock onto the lander's delivery area, it would not have counted for their score. We're 13 and a half minutes, only a minute and a half remaining in this run, and North Dakota at the top of the screen, you can see how deeply their wheels are buried. They have gotten themselves high centered, probably. Their wheels are probably free spinning and not able to do productive work, possibly. But both of these teams have shown different parts of their robots as working properly before some issues cropped up. So I'm very hopeful that both of these teams are going to be able to go back to the robo pit and spend just a little bit of time doing some minor tweaks or some minor adjustments, and then have their robots fully ready, fully capable of competing in their second of two official competition runs tomorrow with only 30 seconds left. This is University of North Dakota and University of Nebraska Lincoln, not quite able to bring back any scoring gravel back to the lander in their first run, but hopefully they'll be able to do so in their second run tomorrow. And as time runs out on these two teams' first run, is telling us that we are going to give teams a lunch break for approximately an hour. Of course, keep this. We're gonna continue to live stream, and so keep our live stream up on your computers and mobile devices, because even though we're being told it is planned to be a full hour, our schedule is very fluid. Even the time that we decide to start back up is going to be fluid. So I'm not going to guarantee, I'm not going to promise the viewers that we're going to be back at a certain time. I'm just going to say we might break for lunch for an hour. It might be longer than that. It might be less than that. So just stay close, stay tuned, and for the latest. The teams that are showing on my screen as running next after a lunch break is going to be University of North Florida and the University of Virginia. And I wish I could give you a list of teams beyond that, but my screen is not showing any teams beyond University of North Florida and University of Virginia after lunch. But I will say that we're going to try and get through all nearly 20 of the teams that are with us today. And at the very end of the day, we might even have some demonstration runs that are not going to be scored, not going to be judged from some teams that have asked us if they could do that. So don't go anywhere. We're going to continue to live stream all day long. We're not going to stop our stream. So don't go anywhere. Continue to monitor this channel. And you are watching NASA's Lunabotics 2022 competition. We are streaming live all day long from NASA Kennedy Space Center's Visitor Complex. See you soon. So it looks like during that run, when we were looking the other way, the North Dakota robot did actually line itself up properly with the lander, and it actually offloaded a nice little load. And we we apologize. We were just looking the other way. We scrolled back in the video feed, and it's right there, plain as day. So anyway, congrats to both teams. That was. They both should be very proud of their accomplishments, and hopefully we'll see some even more amazing stuff later on when they are able to run again.
sophisticate and do the other things, not because they are easy, but because they are hard.
You are watching NASA's Lunabotics 2022 competition. You're seeing a live view from the robo pits where teams are frantically and furiously working on their robots for their run later today. Some of these teams are working on their robots for their second run, which is going to happen tomorrow. We are just coming back from a lunch break, and we have two teams that are getting ready to go into the arena. Those are going to be the University of North Florida and the University of Virginia. And for those watching at home and are interested to find out when their favorite team is going to be running, I can run down the whole schedule for the rest of the day. Of course, this schedule is very fluid, so please be very patient and very understanding as this schedule changes. But right now, it looks like after University of North Florida and University of Virginia, we're going to have Worcester Polytechnic Institute and Oakton Community College. Then we'll have University of Illinois at Chicago and Marquette University. Then we'll have Sonoma State University and San Diego State University. Then the University of Portland and South Dakota School of Mines. Then Montana Tech and University of New Hampshire. Then North Dakota State University and University of Maine. Then Lone Star College Sci-Fair, going just by themselves. And then last run of the day will be two demo runs. We will have University of Akron perform a demonstration-only run, and the University of Arkansas perform a demonstration run. Again, this is the current schedule, which is subject to change. Very highly probable it will change, so don't be surprised if it does change. But I did want to give everyone who's watching at home a heads up as to the complete run, the complete schedule of teams that we are expecting to see in our competition today. And then all of these teams are going to be able to come back tomorrow and get a second official competition run tomorrow. Don't go anywhere, because our very first teams of this afternoon are getting ready to go into the arena. So don't go anywhere, and we'll see North Florida and University of Virginia coming up next. We can now see University of North Florida getting ready to set their robot into our Artemis Arena. Two students from each team required or allowed to go into the arena once they have donned the proper protective equipment, which is a bunny suit or coveralls that keep their bare skin from being exposed to the fine dusty particles of the crushed volcanic rock, and goggles to keep fine dusty particles out of their eyes, and also an N95 mask to keep them from inhaling any of these fine dusty particles. So only two of their students are allowed to come into the arena with their robot in order to activate the robot and verify that it's ready for the run. The rest of the team, usually the rest of the team, go down the hall to our control center, our control room, where they're allowed to sit in a closed room and set up their computer equipment, any monitors they might have, any computers they might have, laptops. And that's where they will be monitoring the status and progress of the robot, monitoring the data that comes back from the robot, and controlling the robot once the competition run starts. What we provide the students between the control room and the Artemis Arena is basically a long Ethernet cable, an Ethernet network cable. And so the students bring a wireless router into the arena, which you can see in the very upper right of the corner is this particular team's wireless router with the two antennas sticking up. The students plug their wireless router into this long Ethernet cable that we supply, and then the other end of that long Ethernet cable is in the control room, and so the students can plug in all of their control equipment to the other end of that Ethernet cable. And then wirelessly, each team's robot needs to connect to each team their own router, and they're given a specific channel number that they must use for their communications. And these channel numbers are chosen by NASA prior to the event and stated into our rules document. The two possible channel numbers these teams are allowed to use during the event, and teams are assigned channel numbers by our pit boss during the scheduling process. And keeping these two robots on different channels, appropriate channels during their run, keeps them from interfering with each other's communication. We just saw at the top of the screen our University of Virginia team has brought their robot into the Artemis Arena and are getting ready to set it onto the surface of our simulated moon. As the University of Virginia team brings a robot into the arena and sets it down onto the surface, you'll notice that both of these teams have chosen a bucket ladder digging system. which is essentially a series of digging buckets that are attached to either a conveyor belt or it looks like chains in both of these cases that rotate around in kind of a linear fashion, like a conveyor belt type of fashion, in order to scoop up the material. And most often, these bucket ladder systems deploy in a couple different ways. The height of these robots are limited when they start out on our simulated lunar surface. But once the competition run starts, robots are allowed to deploy beyond that limited height, and actually in all three directions. They're allowed to deploy beyond their starting width, height, and length. And so a lot of these bucket ladder systems are quite tall because they're designed to lower down beneath the surface while they're digging in order to go very deep. And so you'll notice that a lot of these bucket ladder systems start out laying over across the top of the robot when they start out so that they can meet the limited height requirement for starting out on the surface of the moon. But once they get to the digging area and start digging, you'll notice that they'll be pointing almost straight up and down in some cases in order to maximize the depth that they can plunge these digging implements down into the soil. You'll notice both of these robots have a four-wheel design. Very likely that that each wheel is driven individually, so they're four-wheel drive, usually not just two-wheel drive, and that's often because these robots need four-wheel drive in most cases in order to move around on this very unique material. It can be light and fluffy on top, but it can be very dense, very compact, and sometimes difficult to maneuver in once you get below the very light, fluffy stuff on top. Both of these teams appear to have chosen kind of an open wheel design where no part of the wheel appears to be solid. You've got lots of spokes, lots of air gaps, and that could be an attempt to allow these robots to spin in place and turn, and not bulldoze sideways with their wheels. And so that might manage for a wheel design like this. But there's no one excavation design or even offloading design. Each team has done the research, and a lot of them have probably designed and tried out prototypes of different systems in order to decide which one they ended up going with. And NASA actually gets the benefit of watching and studying all of these different designs that come through this Lunabotics mining competition. And for example, all of our arena judges that are working in the arena full time this week are all NASA engineers, and they're able to watch these robots from very close up. They basically have one of the best views in the world, and they're able to notice things that we might not be able to notice from our vantage point, and possibly take some of the designs that they see here that appear to work well, or that appear to solve a problem that they themselves have been having back in the lab, and discuss those ideas with their coworkers, and maybe try some new things out in the lab that they hadn't thought of before. It's really great that we can, every single year, we can get 40 or 50 lunar mining robot prototypes in here. We get to watch and see how they perform, and we get to do a little bit of a free trade study, so to speak, by watching all these robots in detail and learning lessons from them. Speaking of our arena judges, those are the folks in the on the screen right now that have the more gear that they're wearing, and these are the folks that basically spend all day in the arena, and so they have a full head covering, a full head mask and helmet system that allows them to be able to talk on radios, and not have to talk through a mask, and allows them more comfort for the long duration that they're required to be in that protective equipment. And our afternoon crew, I was talking to them earlier during lunch. We've got Nathan, we've got Evan, we've got Jill, and we've got Brad. And I just want to thank all of the volunteers, these four, the four that were in there earlier, which, if I recall, was Drew, AJ, Tom, and I'm not sure who the fourth one was. Might have been Joe. I want to thank all these folks who are basically taking a break from their day job as engineers out at the Kennedy Space Center in order to volunteer to work our event. Not just the judges that you see on camera here, but literally hundreds of people behind the scenes that you're never going to see on camera, that have volunteered their time to take some hours or days or an entire week in some cases away from their normal day job in order to help us run this competition here this week. We really appreciate all of our volunteers and all of our staff that are helping us make this Lunabotics 22 event a huge success. These students in the arena are activating their robots, and they are communicating using their radios that you can see on the screen to their teammates down the hall in the control room, and talking back and forth, giving instructions. It looks like possibly the North Florida team at the bottom of the screen may be troubleshooting some sort of an issue, possibly. Looks like the student has their hand in while the other student is communicating with the rest of their teammates down in the control room. The Virginia robot at the top of the screen, students appear to be hands off in kind of a waiting mode, so their checkout may be complete, and they may be ready to go. Okay, looks like we are now seeing both sets of teams exit the arena, and we're seeing the judges put the final touches on the arena. And so that means that we will be starting this run between University of Virginia on the left and University of North Florida on the right in just the next few minutes. So don't go anywhere. You're watching NASA Lunabotics competition here at the Kennedy Space Center Visitor Complex in Florida. I just got to say something about my coworker Brad's helmet there. His helmet is the coolest helmet of all. So if there was a helmet contest between all of our arena judges, Brad would definitely win. I don't know if he painted that himself or if that is how he purchased it, but way to go, Brad. You win the helmet contest. Hopefully, this run will start in just the next few minutes. And I just want to mention that this competition, it isn't as easy as just creating a robot that can dig and deposit this gravel that we've hidden beneath the surface. There's a lot of different scoring criteria that are involved in the final scores. So um, the students have to make the students must consider all the trade-offs and try and create a robot that is strong but also a robot that's lightweight. And sometimes those two requirements, don't really play well together. Um, they also need to make a robot that's energy efficient. And again, that kind of sometimes goes against a robot that's really strong. And so there's a fine line that the students um, have to walk in order to find kind of the sweet spot there. They are also they also need to consider the fine dust that that these robots are operating in, and so they need to make their robot tolerant of this fine and very abrasive dust that can actually do damage to their robots if they're not careful with how they design and how they choose materials used on their robots. They also will be judged on how much of a dust cloud will be created during the actual digging operation. And so a robot that that creates this huge dust cloud around it while it's digging will be judged more harshly than a robot that does the same amount of digging but is able to keep the dust cloud down to a bare minimum. And then, as I mentioned earlier, these students will get a lot of bonus points for autonomy. So if students are able to create a highly or even fully autonomous vehicle that doesn't require high bandwidth communication back and forth between the robot and the control center. That will give them an advantage, a points advantage, a scoring advantage in this competition. So there's so many variables involved in all the design choices that these students have to make in designing their robots to compete in this event. And it looks like our timer has started. So these teams are going to get 15 minutes to get the robots out of the starting area, which is we're pretending that these robots were dropped off onto the lunar surface from a lunar lander. And we're almost a full minute into this run for these two teams. So we're hopeful to see some motion, some movement from both of these teams. Looking ahead, our next two teams that are going to be coming up after University of North Florida and University of Virginia are going to be Worcester Polytechnic Institute, or WPI, and Oakton Community College. Saw just a little bit of motion there. The Virginia robot is finally moving. Okay, so it backed away from the starting point, and now it has to turn. Doesn't look like the back wheels are spinning. Oh, yeah, the back wheel just spun. So these robots always seem to work a lot better when all four wheels are commanded and doing productive work. So the Virginia robot is almost turned into a direction that it needs to be pointed. It needs to go through our obstacle area. So it's past the rocks. It needs to go, probably doesn't want to go over that berm. So it's pointing away from the berm. So that's good. We can definitely see some of the wheels spin while some of them don't. So there's possibly a little bit of issues with not all of the wheels being in sync, but it is making progress regardless. So we'll count it as successful. You can have a lot of little problems in this competition and still succeed, but there's so many links in the chain of what it really takes to get your robot to perform this entire mission from start to finish. So sometimes when one of those links completely breaks, that is really bad news for some of these robots if they have one very critical task that they're unable to perform. We can see the digging buckets that are all connected in a row using chains. We can see some motion there on the Virginia robot. And you can see how the angle of their digger can be changed, and also the height of their digger can be changed. Meanwhile, I haven't noticed any motion yet from the University of North Florida robot. There may be some sort of a problem there with that robot. So this Virginia robot has pretty good sized buckets with pretty good sized teeth. It looks to be aluminum, although I'm not an expert in materials, so I could be completely wrong there. So it looks like they're running their system backwards. It's possible they're going to start with the buckets on the other side and then lower their digging system. Now, the students who are controlling this robot cannot see this angle. They're actually kind of seeing the reverse angle from what we're looking at. And so we have a much better view than they do. There they caught a little bit of, oh, that was a big scoop right there. As big as that scoop was, and then they got another big scoop. As big as as full and big as these first scoops are going to be, that's some good stuff right there. There's not likely going to be very much, if any, of our buried gravel, our buried rocks that our judges have buried beneath the surface. So we've made this challenge difficult for these teams in a number of different ways. Teams are going to have to dig far enough below the surface. I saw something. Okay, they've got a conveyor belt that these buckets are dumping their load onto, and it looks like that conveyor belt drove towards the back of the robot, which we saw a little bit ago. As I was saying, we've challenged these teams to not just dig this loose, fluffy, crushed volcanic rock in our Artemis arena. They don't get any points for bringing back this loose, crushed volcanic rock, this loose soil, this fine particle stuff. They have to dig below the surface to a point where they actually find the hidden gravel, the hidden rocks that we have buried beneath the surface, and that's the scoring material. That's why the lander at the far end of the screen, the lander is actually a mesh where the fine particles will fall through, and only the larger rocks, the gravel, will remain to be scored by the judges. It's like Virginia's going really deep now. They've put their excavation system way down deep, and they're bringing those buckets around. Okay, they're pulling up a little bit. I'm not sure why their bucket ladder system didn't go all the way around. One of their buckets may be hitting something on the other side, or something at the top of their. Let's watch as it goes around. Let's watch and see if it binds. There was the top bucket dumped. And then their conveyor belt just moved, because they're really not interested in keeping this initial top level dirt. They might be hitting something right there that keeps them from going further. We are 9 minutes into a 15-minute run, so 6 minutes remaining for these two teams. This is their first attempt, and each team that is competing with us here this week is going to get 2 official runs. Looks like Virginia is possibly having enough issues with their digging system that they're going to go ahead and head back to the lander just to possibly get some run time and some test time on their offloading mechanism. You can see when these wheels spin and aren't actually able to make productive movement out of the robot, When a wheel spins in this material, this light fluffy material, it can have a tendency to dig in and get your robot buried a little bit. All right, you can see their dump mechanism. Oh, look, a rock came out. You can see the body language from the student on the other side of the class. Yes, at least one rock came out. It's hard to tell from this camera if there was more than one rock that came out. But for the first attempt, for a team that has not been able to compete in this competition for several years. Oh, I think I see another rock that hasn't come out of their dump bed. Oh, if only it raised up a little bit more. I think there's come out. We're down to 4 minutes remaining in this 15-minute run for these two teams, University of Virginia and University of North Florida. This is their first run. They'll get a second attempt tomorrow. All teams are going to get 2 official attempts in the arena this week. Now, for those that have watched or paid attention in past years, you might recall that we have spent, I believe, our entire first day letting teams run in the arena as just for practice. And this year, we have made this competition more challenging, and we have decided to not let teams perform any practice runs inside the arena. So the very first time these robots ever enter the arena, they are there for an official scored competition run. And they'll get 2 of those official competition runs here this week. 3 minutes remain. Sadly, we have not seen the University of North Florida robot move, but hopefully the students have been able to troubleshoot the issue. Hopefully they know what is going on, and hopefully they will be able to correct whatever that issue is and come back for their second attempt, their second run tomorrow, and have a lot of success. 2.5 minutes remaining. So just to look ahead, our next 2 teams after University of North Florida and University of Virginia, our 2 next teams are going to be Worcester Polytechnic Institute and Oakton Community College. After that, we should see the University of Illinois at Chicago and Marquette University. 2 minutes remain. That was a good solid load. Just something appears to be keeping that train of buckets from going any further than that. Okay, so what are the odds that in the next 1.5 minutes, this Virginia robot is going to be able to get back to the starting place and dump another load? Hopefully, there's another few rocks on their screen. Their onboard hopper is just a complete wire mesh. It basically it ignores all of the fine powder material and only holds on to the rock. So they've got a full minute left. Should be plenty of time for them to dump whatever they have on board. And let's see, I think we saw a few rocks. I think we saw some. So what are they going to do now? Are they going to try and dig some more? Or are they going to just have some fun and do some donuts in the arena, or just chill out and just be content with what they've done? They should be happy. They've done multiple cycles back and forth. Even though their robots seemed to have some issues with their digging system, they were able to work through those issues and and have some success. Are they gonna make a run for the berm? We've seen several teams do that at the end of their run. Look at that, they went over the berm. And the judges are very happy for them. Good job, Virginia. So with enough energy, with enough speed, um, I suspect that a lot of these robots would be able to get over that berm. And as time runs out, on University of North Florida and University of Virginia, congrats to both teams for getting this far, and good luck on your second competition rounds tomorrow. So as the student teams come back into the arena and remove their robots from our Artemis arena, um, we will look forward to seeing Worcester Polytechnic Institute, WPI, and Oakton Community College coming into our arena next, followed by the University of Illinois at Chicago and Marquette University. So do not go anywhere because you don't want to miss 2022 event. We are live streaming. Tell all your friends about this live stream. Share it on social media. Um, and if you're interested in watching our Monday and Tuesday live streams, where we went through about half of our our student teams that are competing here this week, you can go to our main website, nasa.gov/lunabotics. You'll see a link there for this live stream that you're watching right now, but you'll also see links for our Monday and Tuesday live streams that you can go ahead and watch uh, the replays from those live streams. So don't go anywhere. Coming up next are WPI and Oakton Community College.
Innovation is at the core of our work at NASA. It determines where we're going and how we'll get there. Innovation created the first mission to Mars. It allowed us to study the solar system beyond the sun's influence, and it sent the first humans to the moon. Innovation helps NASA take giant leaps in our work on space exploration, aeronautics, and earth science research. It saves money and time, increases performance, and creates higher quality work. But what is innovation? It begins with an idea for how to solve a problem, but that is only the start. True innovation is perspiration and perseverance. It is months and years of hard work by teams of people working together. It is more than imagining a solution. It is making that solution a reality. Innovation is building, shaping, and refining an idea. It is using existing technology in new ways to maximize impact. And true innovation moves beyond linear growth. True innovation is exponential growth. It is finding new spaces to grow into, new niches to explore, new resources, and new ideas. It is connecting the dots. At NASA, we know innovation isn't created by one person alone, and we know it isn't created by one team alone. That's why we propel our mission through open innovation. Open innovation invites the best creative minds from across the world to work with us to solve some of our most complex problems. We know the more minds we have working on a problem, the better chance we have of true innovation, of exponential growth. Open innovation amplifies the work we do. It solves problems in ways we could never imagine, and it develops solutions that can change the world.
You're watching NASA's Lunabotics competition, streaming live from NASA's Kennedy Space Center Visitor Complex, and we are seeing our next two teams come into the arena for their first attempt of two attempts this week. On the right, we're going to see WPI, Worcester Polytechnic Institute, and on the left, on the B side of our arena, we're going to see Oakton Community College. This will be the first time any of these robots have been placed into our arena this year. None of these students have been able to practice in the arena this year, and so it's a little tougher than past years where they've been able to have that practice time. So there are a lot of challenges the teams have to overcome in order to have a successful run and to have scoring gravel placed into the lander's hopper. You just saw one of the WPI students reach in with their blue glove there and gently touch the surface of our crushed volcanic rock. As I was explaining earlier, this stuff has some very unique mechanical properties. The very top layer is very light and fluffy, and you can see the fingerprints, the handprints that were left behind by that student. But once they got down a certain distance, they probably felt how tough and hard the material, the surface was. It's almost like a hard-packed surface below a light, fluffy soil, and it's definitely a challenge to design and build a robot that can successfully handle driving on, turning on, and digging in this very unique material. Notice how clean and shiny both of these robots are. I suspect after they've dug in the simulated lunar soil that at the end of this run, they won't look nearly so clean and shiny as they do right now. What I suspect is happening right now is that the judges in the arena are communicating with the judge in the control room where the rest of the student teammates are located, and verifying that the students in the control room are all plugged in, all of their equipment is basically ready to go, and then they will start a timer and allow the students to activate their robots, which I think just happened. So we've got a 5-minute timer that has been started by our judging staff. And now both teams have 5 minutes to activate their robots and communicate with their teammates, the students that are in the control room down the hall, they're communicating using a walkie-talkie. And they have, during this setup time, to verify that everything is working and then that the robot is ready to perform. Teams are also allowed to use this time to set up and install any sensors or transmitters that they plan to use that are located at the lander. And sometimes you'll see student teams set up visual indicators, visual markers. Sometimes you'll see them set up radio transmitters or some sort of a transmitter or some sort of a sensor onto the lander location that the robots can then use during their run in order to help out with understanding where the robot is, or to help out with any autonomous design that robot uses. So the WPI robot on the right appears to have a bucket ladder system that is right now flat on top of the robot, but will probably see later will deploy more vertically in the front of the robot, like we've seen other robots use. The Oakton Community College robot on the left is a little harder to see. Looks like there's a motor sticking up out of the middle of the robot. I could be wrong, but a lot of times motors are cylindrical in shape and have wires coming out the rear end. So that could be a motor. It could be an auger. Seeing a little bit of motion from the WPI robot during their setup time, and so the students are communicating with their teammates. Oh, we saw a little bit of motion from the Oakton Community College robot too. So that's usually a good sign when we see a little bit of motion from the robot during their checkout period. And so that gives us hope that both of these robots are going to be able to operate without issue, at least communication-wise, everything checks out. Both of these robots, what I was going to say about the motor in the middle of the Oakton robot is it's possible that it's an auger, although we'll see when it starts digging whether that's true or not. It could be. There's a lot of different digging mechanisms that could be employed here on this robot. What we've seen is the students have left the arena, and looks like this run has started for Oakton Community College on the left and Worcester Polytechnic on the right. Oakton's robot has backed away from its starting position. Seems like one of the wheels is moving a little bit more than the others. So I'm not sure if there's some slipping going on with the other wheels, between the wheel and the axle. There's so many things that could cause, a problem here. A wheel could be slipping on its axle, and its axle could be turning, and the outside wheel not actually turning. Uh, Another problem could be that they're just not powered. They just don't have the power to do the work. You can see as the Oakton robot started turning to the left, that front left wheel started pushing or bulldozing some of this top layer of fluffy regolith, which can be tough for some robots. So it can turn to the right. You can see it's really powering. Both of its rear wheels, which are now on the left side of the screen, have not given up, even though it's bulldozing a little bit. It's powering through it. So at least in this direction, this Oakton robot appears to have enough power. I was about to say, I wonder if it's stuck, because it's really, really close to the lander. Matter of fact, it's the nose of the Oakton robot is actually underneath the lander's screen, and we just saw the WPI robot pull away from its starting position. This is a good camera angle, because we can see both of them, and we can actually see their tire tracks. Now the WPI robot at the bottom of the screen has a unique suspension system that keeps everything keeps the rest of the robot fairly high off of the surface compared to some of the other robots we've seen in this competition. All right, WPI has started to exit the starting area. WPI at the bottom of the screen, you can see it's able to do a little bit of spinning in place, but when it gets a little bit stuck, because it's bulldozing its wheel and into this material, and the material ends up building up to a point where it's strong enough to kind of stop the robot's progress. You've seen by their wheel tracks that this WPI team goes ahead and tries a 3-point turn, for example, which might work better for them than spinning in place. Now, I suspect this WPI robot on the lower half of the screen has enough ground clearance to just drive right over that berm, but the students may be, it may be a little early for them to risk that. And then we see the Oakton robot wake up again, but it seems like it may be out of control. We just saw the judge reach over and hit the e-stop, so that's going to be where the Oakton robot sits for the rest of this run. I'm afraid they've been disabled. And look at WPI, not afraid to drive over that berm. This is a really good view for berm watching. The robot is bottoming out a little bit, but let's see if WPI is able to get the robot over. Yep, and right into a crater, but I don't think this robot is going to have any trouble getting past that crater either, based on its unique suspension system and its large ground clearance. Okay, so this is WPI on the right. Almost 5 minutes into a 15-minute run for these teams. Let's see. WPI looks like they've got some web cameras. One on the very front of the robot. We can see the web camera rotating and actually panning to the left and right, but we also saw it aim itself downward. I don't know if the students are watching these webcams in the control room and manually driving this robot, or whether this robot is being automatically controlled by onboard software. Only the students in the control center and their judge, who is sitting in the control center watching them and monitoring them, know whether they're manual or automated. So WPI has raised their digging mechanism, which looks to be a belt, like a conveyor belt, with, I guess you would call them buckets, although it looks like they're open. So let's see if this WPI robot is able to dig. Its bucket ladder system is spinning, and you can see by the body language of the students outside the arena that maybe they should spin it in the other direction. There you go. Now I suspect that the students will be lowering it. And I've said this before, but it's worth repeating. The students that are operating this robot from the control room, they don't have the benefit of this particular camera angle, but they do have several cameras on board their robot that I suspect they're monitoring those feeds. So I suspect that the students in the control room could immediately see that everything, that their digging mechanism was spinning in the wrong direction, for example. Looks like they've got a really good view using this front camera pointed down. It looks like they've got a really good view of their digging. You can see it's slowly but steadily plunging down below the top of the surface. And so we should see in the next few moments some progress, some digging progress for this WPI robot. You can see a little bit of dust, a little bit of dirt, soil being flung out in front of the robot. Once they get a little bit deeper, they should be taking some bigger bites. And yeah, we can start to see some soil going up the elevator now. Oh, and from the side view, it looks a lot better from the side view because you can actually see it spilling out on board the robot. And so they've got two sets of bucket ladder systems. One is doing the digging, and then it's dumping to a second stage where I don't know. I suspect they may be doing the separation of the fine particles and the larger rocks. The overhead view is kind of interesting. It's still a little bit hard to see though. You can see fine dust piling up towards the back of the robot. What I'm wondering if we'll be able to see from this angle though is what happens to the larger rocks. Are they going into a separate spot on board the robot, or what? How will they get separated? Or is it possible that those get separated just during the offloading portion of their system? You can definitely see a couple rocks here and there on the robot, which is exciting to see. Oh, look, there's some big rocks coming up. Look at that. Look at those rocks. Only 5.5 minutes, 5 minutes and 20 seconds remaining in this run. How long is WPI going to continue to dig, recognizing that they're making really good progress? They're bringing up some rocks. I assume that the students are able to see these rocks coming up that conveyor belt using their on cameras. It's possible that they may be using the NASA provided lander situational camera too. Only the judges know which cameras they're using. There's another big rock. Look at that guy. So at what point, with 4.5 minutes remaining in this run, at what point is WPI going to say, okay, now we need to stop digging? Because look at the body language of the students on the left. They seem they've got to be happy seeing this robot making this progress, but I wonder if they can see how much time is left. I've got 4 minutes and 15 seconds remaining on this run. So how long does this robot need in order to lift its digging mechanism up out of the soil? It is going down very slowly, but can it come up very, very quickly? Does it have 2 gears, for example? Or is it going to come up very slowly as it went down? Let's see how quickly this digging mechanism can raise itself up out of the surface of our simulated moon dirt. We have 3.5 minutes remaining in this run for WPI. So even if it takes a couple minutes to raise this digging system up out of the surface, did it stop? Okay, they're rotating it. At some point, they don't have to raise it all the way up if they can rotate it up out of the way. There you go. Okay, so now they've got 3 minutes left. This is exciting because the robot didn't take very long to get down here to the digging area. So in theory, it shouldn't take very long to get back. Is it going to go over that berm, which is a little bit risky because there's more weight. This robot weighs more than it did before. Now I'm wondering if this robot is autonomous, because if I was stick driving this robot, I wouldn't be paused right here. I wonder if they are stick driving it, if they've maybe lost connection somehow, and the robot is stuck on its last command. I would hate for this team to get this far and then not make it all the way back. We're down to 2 minutes and 20 seconds for this team. Okay, time is running a little bit short with only 2 minutes left. WPI, Worcester Polytechnic Institute. Everybody is cheering for them. They had a really great dig. It would be so